Hello everyone, I'm Professor Neerav Mehta from Institute of Technology and Engineering. Today's session, we're going to discuss about subject called automobile system design. In this particular video, we will discuss about design of coil spring suspension system. For that, we have to design a spring for particular suspension system. From GTU, according to our GTU syllabus, you will ask to have design this kind of suspension system which could have helical spring suspension. For that, we have to design this helical spring as well as you will ask to have those example for this helical spring. So let's discuss about this helical spring. Clear? So this is nothing but design of helical, or you also can say coil spring. Clear? So what is this coil spring? The spring is a design defined as an elastic body whose function is to distort when the loaded and recover when original shape when its load is removed. So ultimately, the function of the spring, which we have discussed in previous session, to absorb that kinetic energy and recover that kinetic energy or dissipate that particular kinetic energy when load is removed. This could be used as a shock absorber. Clear? In the brakes, you can use this, could be in a brake, in clutches, as well as in the case of our suspension system, in case of cam and follower. There are multiple uses of this spring, but in this particular session we will discuss about this spring according to our suspension system. So first of all, let's discuss about different terminology of the spring. The first thing to discuss about is solid length. What is the solid length of a spring? So when a spring, there could be two types of extension or a deflection of a spring. One could be in tension and one could be in compression. In the case of suspension system, our deflection would always going to be in negative direction, so which is called compression, and the maximum compression which could attain the spring is called its solid length. So first thing here is discussion of solid length. If the number of turns in a spring is endless and the thickness of the wire, because spring is nothing but a wire is wounded in helical shape, that is called a spring. So when we are compressing this spring to its maximum point, here it will attain that solid length. And this solid length is represented by its number of turns into its wheel or sorry wire diameter. So ultimately, solid length is nothing but number of turns into wire diameter. That will going to become its solid length. Second thing, which is free length. What is this free length? When we are removing any kind of force from our spring, then it will attain that maximum length without any stress or a force, that is called free length. This free length could be represented by this solid length plus maximum deflection plus clearance. Here in this case, clearance could be represented by 0.15 of deflection or maximum deflection. This is empirical formula, clear, but the part which is free length plus solid length is a geometrical formula. So this total formula is combination or formula of free length is a combination of geometrical formula as well as empirical formula. Geometrical formula could be represented by solid length plus maximum deflection plus 0.15 of maximum deflection. We are going to use this same equation for our example. That could be a different equation also, where you can replace that 0.15 into delta maximum by n minus 1, which is represented by this number of turns. So you can have this both of this equation to find out free length, but we will have that first equation for our examples. Clear? Third thing to understand is spring index. This spring index is most important terminology in our spring, because in industries when we are about to or able to ask to find types of spring, then we have provided by spring index. Spring index is nothing but a ratio of mean diameter of spring to the diameter of wire. Once again, spring index is the ratio of mean diameter spring to the diameter of the wire, which is represented by capital C, where it is capital D by small d, where capital D is mean diameter of spring and small d is a wire diameter of the spring. I hope you got this idea. Then the spring index which is small k, it is also called the stiffness constant. Here, which could be represented by load upon its maximum deflection, or you can also call it as a spring rate. Clear? The unit for the spring rate will be in terms of Newton per mm. You can represent it by the maximum number of or amount of deflection for particular load. Clear? That is called spring rate. Then pitch of our spring. What is the pitch of our spring? Pitch of our spring is nothing but distance between two consecutive spring coils, or two coils difference or distance between two consecutive coil, which is represented by free length divided by number of turns divided minus 1. Clear? Because from the spring you can see that the spaces between the count of spaces between those spring could be represented by n minus 1. So once again, pitch could be represented by free length divided by number of turns minus 1. I hope you got this terminologies, because this terminology will going to help you to find design of spring in the when we are having those examples according to this. So next part is to design of stresses in spring. Basically, spring is nothing but a wire. So this wire will goes under twisting moment. This twisting moment will absorb or will reflected as a linear deflection in the spring. Or you can say this linear deflection of the spring will transfer to the twisting moment of that wire. So we have to find shear stress. There are two types of shear stress will induced in our spring. One is shear stress due to twisting and another shear stress due to direct loading. So from the equation which is T by G is equals to tau by R, we can find this equation where T is nothing but W into D by 2, which is represented by twisting moment, which is equals to pi by 16 shear stress into D raised to D cube. Clear? So ultimately, shear stress due to this load can be represented by 8 WD upon pi D cube. And in the case of direct stress, it is represented by, which is T2, which is or shear stress number 2, which is represented by load upon cross section area, which is 4W upon pi d square. Clear? By combining these two, we can find total shear strength. Uh, this could be represented directly by this equation, where a constant which is called Wahl's factor, which is represented by shear stress into K into 8 WD upon pi d cube. So where K is nothing but 4C minus 1 upon 4C minus 4 plus 0.615 upon C. This value will going to be constant for each and every example and each and every derivation, where C is nothing but R spring index. Once again, for this design, we have found two types of stress. One is shear stress due to twisting and one is shear stress due to direct loading. From that, we have developed this final equation, which is total stress, which is K into WD upon 8D cube. In terms of C, it is K into 8WC upon pi d square, where K is nothing but a Wahl's factor and value is 4C minus 1 upon 4C minus 4 upon plus 0.615 divided by C. You can find C from D divided by D, which is capital D by small d. Clear? I hope you got that design of stress in spring. Next point, this deflection, because ultimately this absorbed energy or this absorbed stress will be converted to deflection. Clear? Here you can have this maximum amount of deflection in terms of, first you will have this deflection in terms of theta, and then we will have this deflection in terms of delta. So ultimately deflection delta or linear deflection. In terms of angular deflection, it is represented by delta is equals to theta into d by 2. Clear? Here first we will have this equation t by j is equals to tau by r is divided by d by 2 into g theta by l. This is a twisting moment equation where we have this combination of these two, t by j is equals to g theta by l, where we can find angular deflection. How this angular deflection takes place, in previous slide we have talked about that twisting moment. This twisting moment will convert to twisting of our wire, and this twisting of wire is just because of deflection which is caused by that linear moment of our spring. So linear moment is represented by theta into d by 2, where we are going to find this theta from that twisting moment and shear stress and rigidity. So ultimately theta will be t into L by G by G, where G is modulus of rigidity, J is polar moment of inertia, which is pi by 32 d raised to 4. L is nothing but total length, which could be represented by pi d n, and twisting moment is W into d by 2. So ultimately we will have this equation of theta is 16 W d square n upon G d raised to 4. This equation, we will convert this equation in terms of delta, because in each and every example we will be given by this linear deflection rather than angular deflection. So we have to convert this linear deflection in terms of angular deflection. Sorry, angular deflection in terms of linear deflection. So our angular deflection here is 16W d square n divided by gd raised to 4, which is multiplied by d by 2. So ultimately we will have equation 8w d cube n divided by gd raised to 4. Let's convert the d cube upon capital D cube upon small d cube into c cube. So ultimately 8w c cube n upon gd, which is also called deflection of our spring, or a linear deflection of our spring, where c is nothing but d by c. Clear? I hope you got this point. So ultimately you can have this equation in terms of delta. If you are asked to find delta, you can have that easily, find that delta. Clear? I hope you understand this point very well. We can have this ratio of load upon deflection, which is also called constant K, which equals to GD raised to 4 upon 8 D cube, and so ultimately we can have this 2 as a constant. I hope you understand this design very well. What we have done, first of all, we have find shear stress from that equation, from this equation, and then we have find this deflection in terms of angular deflection as well as linear deflection. So these are the basic formulas to find or to design our spring for our suspension system. I hope you understand this session very well. If you are have any doubt regarding to this, you can ask me. For this particular topic, I have taken reference as a motion design by R.S. Kurmi. Okay, if you have any doubt regarding to this particular session, you can directly ask me. I'm stopping here. Thank you. Thank you so much.